I am so excited to be with you for the SUMS conference at James Madison University. I know that the meaning of being with you and at James Madison University continue to be a bit different, but I'm so grateful to get to share with you the big ideas of computability theory, my area of research. I do hope that someday I get to visit the beautiful Shenandoah Valley where James Madison University is located. The views from campus look truly amazing and so much better than those in my basement, which is where I currently am. I do hope I also get to meet some of you in person on the day of the actual live part of the conference. And I also want to thank the organizers, Peter Cohn and Roger Thelwell, for all the work that they've done to figure out how to make SUMS happen this year. That's a real feat. So let's get started. Today, we'll be climbing through trees, though I don't mean the kinds of trees that you would see in the Shenandoah Valley. And I'll say what kind of trees I mean in just a bit. But overall, what I'm really trying to do is to give you insight into the idea of measuring the complexity of different mathematical problems. So mathematical theorems often take what I consider an existential perspective. So a mathematical theorem often asserts that given a particular scenario, a specified structure exists. So let me give you an example of a theorem, and I'll explain what all the words in this theorem are saying later, but for right now, just look at the big form of the theorem. So this result is called König's lemma, and it says that every infinite binary tree has an infinite path. So notice this is another existential perspective kind of result, because it says given any infinite binary tree X, there is an infinite path Y through X. Well, if you have such a theorem, you can associate with it a problem. And specifically, what do I mean? Well, you can think about a particular scenario that you're considering in the theorem as an instance of the problem, and any specified structure Y related to that scenario that satisfies the desired properties, you can consider a solution to X. So let's let the problem WKL, standing for König's lemma, correspond to that theorem of König's lemma. Well, what we're going to be talking about today is trying to calibrate problem complexity. So a first question that we might have is, all right, this problem of finding paths through trees, is that problem computable? If I have some kind of computable binary tree, well, can I actually compute an infinite path? We're going to see together that WKL is not computable. But, well, then just how hard is it? Is it just a little bit not computable, or is it super bad? And to address this question, we're going to take a few variations on an oracle approach. And by oracle, I mean sort of, well, what information would it take to solve this problem of WKL? And so you could just think about what information do you need, but you could also more specifically think about, well, can I reduce this problem to other mathematical problems? And by reduce, I mean, well, can you transform the problem of finding paths through trees into some other problem whose then solution would allow you to find the desired paths through trees in WKL? Well, before we can address any of these questions, we should start with, well, what do we mean by to compute? So Alan Turing formalized what it means to compute in 1936. And for the purposes of this talk, we're going to take advantage of the useful anachronism that his model of computation was a computer that can run what are now known as Turing machines. You should think of a Turing machine as a computer program, a finite set of instructions that is deterministic and uses natural numbers for inputs and outputs. So I'm going to call a function, which takes in natural numbers and outputs natural numbers, computable, if there is a computer program that when run on input n, halts and outputs f of n. Well, maybe we should say a bit more again. What do I mean by a computer program? again, for our purposes, think of about a computer program as a finite set of instructions, deterministic instructions. So you know how to get from one step to the next in some computer language. Pick your favorite one. Say it's Python. Well, one of the cool things about viewing a program this way is actually, when you think about it, then there is a computable list, I'll say P0, P1, P2 of all programs out there. How do you get this list? Well, one thing you could do is you could just list all the finite sequences of symbols used in Python, ordered by length and alphabetically, and then let PI be the ith finite sequence of symbols in this list. Now, of course, you might be saying to yourself, yes, but these are supposed to be computer programs, and most of what you've just put in your list is totally garbage and would certainly not compile if you've ever programmed. And I agree with you. Most of the list, the programs in this list really are garbage. But if there was any program that you actually would write to do something, will appear in this list somewhere. So the power is that we have a computable list of all the programs. Yes, most of them are garbage, but we are guaranteed that we have all the ones that we are interested in. So you can kind of think about this if you've heard the analogy of, oh, you have a bunch of monkeys typing on typewriters, and eventually you'll get Shakespeare. That's very much in line with this proposition. So one thing that you get for free from this proposition is the fact that there are non-computable functions from the natural numbers to the natural numbers. And why is this? Well, one can show, and don't worry if you don't know this fact, that there are so many functions from the natural numbers to the natural numbers that you can't actually list them all out. And so the word for this is that there are uncountably many functions from the natural numbers to the natural numbers. But we do know that there is a countable list. There's a computable list of all programs out there in the world. Well, so that means that not all functions from the natural numbers to the natural numbers can be computable, because if they were, well, then we would sort of be covering them all with this list of all the programs in the world. But we know that there are too many functions out there for them all to be described by some program. So basically, because there are just too many of these functions, we can conclude that there will have to be non-computable functions from the natural numbers to the natural numbers. If that argument didn't resonate with you, it's because it's really an existence argument, right? We're just saying that, well, somewhere out there are non-computable functions in the world. So it'd be nice if we had a specific function that we could point to and say, hey, this thing is non-computable. Well, the good news is I can tell you and point to a particular non-computable problem that you are likely very familiar with. So if you're a Mac user like me, you sometimes maybe get this spinning beach ball of death. If you're a PC user, I believe it's a blue circle that kind of spins around. And the problem when you see this spinning beach ball is you sort of have to decide, well, when do I just quit out of this program, or even worse, shut down my computer and restart it? Or maybe should I just wait a little bit longer and it'll come back and I'll be able to save that email that I'm writing? Well, so this problem of deciding whether a program is about to halt or not is a non-computable problem. So it's called the halting problem. And what it asks is, it says, well, if program PI is run on input N, does the computation halt? So a solution to this problem would be the following function. We can encode the halting problem as the function from natural numbers to natural numbers, where for an ordered pair of numbers I and n, we're going to output 1 if there is a stage S at which PI halts on input n. And otherwise, this function is going to output 0. So notice that this definition is actually an existential definition itself, right? We're going to output 1 if there is some stage S at which this program PI halts on n. So one can show we won't do it here, but you could think about how to do it. One can show that this function from the natural numbers to natural numbers is not computable. So that's telling you that the halting problem is not computable. Because if it was, well, then we could actually compute this function too. So now that we have an idea of what it means for a problem to be computable, let's return back to thinking about König's lemma and what that theorem's all about. As I mentioned before, the trees in König's lemma are not like the trees that you see in your backyard. So what kinds of trees are they? Well, for us, they're going to be, at least at the beginning, binary trees. And you can think about a binary tree like a family tree. So here at the bottom is Sigmund Christoph Graf von Zeil and Trachtberg. And then connected to him are his two parents. And then each of his two parents have two parents, and so on in this tree. And so this is going to be the kind of tree that we're talking about when we look at König's lemma. So let's be even more specific by what we mean by a tree. So for us, a binary tree T will be a set of finite sequences of zeros and ones. And each one of those sequences is called a node on our tree. And it'll have the following closure, downward closure property. Specifically, if you've got a prefix tau of some node sigma, which is in the tree T, well, then we know that tau is actually also in the tree. So for example, I know that 0, 1, 0 is a node sigma in the tree, and it has its prefix 0, 1. So that tells us that 0, 1 will also be in the tree, as will the prefix 0 of 0, 1, 0. And it's this last property that gives us this tree property of branching that we're looking at. Notice that being a binary tree is why we're using zeros and ones. That's giving us the fact that you're branching at most in two directions at each level. Well, so what's an infinite path through a tree? Well, an infinite path is an infinite sequence, little f, of zeros and ones, such that any finite prefix of that infinite sequence is on the tree. So for example, if we're looking at this binary tree, well then by these ... I'm meaning that we have an infinite path that starts with a 0, 1, 0, 0, et cetera, that goes on forever. And also we have an infinite path that starts with 1, 1, 1, 0, ... And of course, by an infinite tree, what I mean is a tree which has infinitely many nodes in it. So notice, certainly, if you have an infinite path through your tree, you will have infinitely many nodes. So let's now prove König's lemma, prove the statement that we originally saw. Well, it says that every infinite binary tree T has an infinite path F. So let's now prove König's lemma, which said that every infinite binary tree T has an infinite path F. Right? We just saw that if you have an infinite path, certainly you're an infinite tree, but this is saying the other direction. Well, for a proof, let's imagine that we're given an infinite binary tree. And now our job is to find an infinite path through that tree. So, well, we're going to start at our root, and then we have to decide, are we going to go in the 0 direction or the 1 direction? Well, if I ask the question, are there infinitely many nodes down over here, or are there infinitely many nodes over here? That will be good information about which direction should I go in. I certainly don't want to go in a direction where there's only finitely many paths below, because an infinite path requires infinitely much space. So let's imagine that in this direction, there are infinitely many nodes. We know that there has to be one direction which is infinite, because this is an infinite tree and we've only been at this top node at first. So certainly one of these directions will be infinite. So let's of course go with the infinite direction. So that was the 0 direction. Well, now that I'm at this node, which direction should I go in? Well, I know there's infinitely many nodes below, so I can ask which way of going to the left or going to the right will continue to give me infinitely many nodes below. And let's imagine that now below 0, there are infinitely many off to the right and only finite many off to the left. Well, then I'm going to go in the direction of 1, and then I'm going to repeat. So I ask again below 0, 1. Well, which direction are there still going to be infinitely many nodes below me, knowing that at least one of those have to be true? Well, I might find out that there are infinitely many nodes below both the left and the right direction. So if that happens, I can flip a coin, or I can just pick my favorite of 0 and 1, and I can keep iterating this process to obtain an infinite path F. Now, I should say we just showed König's lemma is true, that for every infinite binary tree T, there is an infinite path through the tree. But in fact, this same argument that we just gave holds for any fixed arity of a tree. So if you had a tri-array tree, or a tree with at most 4 branches at each level, the same exact argument works. So now that we know what the theorem König's lemma says, let's go back to thinking about whether the problem of WKL is computable. So remember, that would be saying, given a computable infinite binary tree T, is there a computable infinite path F through that tree? Well, we should be a bit more precise about what do we mean by a computable infinite tree, and what do we mean by a computable infinite path through the tree. So for ground rules, a tree is computable if there is a computer program that, given some natural number L, outputs what the finite subtree of the given tree looks like for all nodes of length less than or equal to L. So you can you can compute what does this tree look like up to a given level for any given level. Then to compute an infinite path of F means what you think is, means to algorithmically determine F of S, the S digit of F for all S in the natural numbers. Well, let's think about whether WKL is computable or not. So if it's a computable problem, there would mean that given some computable infinite binary tree, we should be able to compute a path through it. So let's try and give an algorithm for finding a path given such a tree. Well, if I'm going to be looking for an infinite path through my tree, a natural thing is to first just start by computing some amount of the tree. Let's compute the first 3 levels of the tree just to get a sense of what this tree looks like. So if this is the first 3 levels of the tree, well, I'm certainly not going to go this way, 0, 0, because I can see that there are no nodes over there. So the question is, which direction should I go? I'm certainly going to go here, here, or here. But let's imagine I now go to 0, 1, 0. And maybe these nodes keep growing for a while. But the problem is, maybe this potential path I've started here dies off sort of after I've already committed to starting with 0, 1, 0. So the real issue is that potential paths can die off kind of late in the game. And I can find out later that, oh, wait, the infinite path or where the tree was infinite was really more over here below these nodes. So this is suggesting that maybe there isn't an algorithm for computing infinite paths through computable infinite binary trees. Well, to prove that it's not computable, what we really need to do is build a counterexample. And by that, I mean a computable infinite tree T, which has no computable infinite path. So the easy part of doing this is to build the tree computably. So what we're going to do is we're going to describe an algorithm that at stage S tells us exactly what the tree looks like through level S. Because to remember, for a tree to be computable, you just need that algorithm which says, okay, you give me an S, I'm going to tell you what it looks like through that level. The other thing that we need to do is we need to build this tree so that it has actually infinitely many nodes. So to do that, we're going to make sure that each level of the tree has a node, And then because there are infinitely many levels, we'll know that our tree is infinite. Now for the hard part, we need to ensure that this tree has no computable infinite path through it. Well, how are we going to do that? Well, what we're going to do is we're going to have requirements for our program to ensure that we have no computable path through it. And we'll actually have infinitely many requirements, one for each program PI. And what the ith requirement says that, well, if program PI is computing Fi, an infinite sequence of zeros and ones, well, then we need to make sure that this infinite sequence Fi computed by PI is not in fact a path on our tree. So to not be a path on our tree means that we need some prefix of Fi not to be on the tree. So in order to describe how our algorithm is going to work, I'm going to talk about our strategy for ensuring that F0, the sequence that's computed or partially computed by the program P0, won't actually grow into an infinite path through our tree. So we'll talk about just the strategy for F0 and P0, and then at the end I'll talk a little bit about how you put these strategies together when describing your algorithm. So we begin building our tree T as a full binary tree, which if you think about what we're trying to do, just build a tree with no computable infinite paths seems like a terrible idea, but that's how we're going to start. And then let's imagine that P0 computes the first digit of its potential path F0. And let's say that 0 is the first digit of that of F0. Well, by the time that P0 computes this first digit, we'll have built the tree up through some level, say level 2. And let's imagine that here's what our tree looks like through level 2. And remember, we're building as a full binary tree. So if we see that F0 starts with a 0, we can't change anything that we've done, but we can stop building the tree below any nodes which begin with a 0. And so that's what we're going to do. We'll just continue building our tree below the nodes that don't start with a 0, and we'll stop building below the nodes that we've already put on our tree that start with a 0. So then, because F0 started with 0, it can't be a path through our tree. Well, then we're just going to keep building our tree until program P1 computes the first 2 digits of F1. And so let's imagine that its F1 starts with a 1 and then a 0. Well, then we could stop building below these nodes and keep building below here. And then we'll repeat this process for all of our different programs. So this certainly will ensure that all of the PIs are not going to compute paths through our tree. But also you should check that by using this algorithm, that our tree is in fact infinite. And specifically that there will be at least one node at each level of our tree. And just as a hint, that's why we watched for P1 to compute the first 2 digits of F1. We're requiring that any given program PI computes at least I many digits of its potential path before we go and kill it off. Now, I should also mention, if it's making you a little nervous, that I'm doing this in order of first watching what P0 does, and then P1, and then P2, you should be nervous. Okay, I'm glossing over how you'd really want this strategy to work, just so it's a little bit easier to understand. What you really want to do is you sort of want to watch what P0 is doing for a while, and then sort of intermix that with what P1 is doing, and then so on with the other strategies. You don't actually want to wait for for P0 to actually compute its first digit of F0, because you might end up waiting forever for it to do that. So there is some extra bit that you need to talk about how to do this counterexample. But when you put all these together, right, we now have a view of König's lemma from the computable perspective. So we proved that König's lemma is a true classical theorem of mathematics We know every infinite binary tree has an infinite path, but we've seen that this theorem falls apart from a computable perspective. So we proved that there is an infinite computable binary tree with no computable path. And this was a result of Kreisel's. He proved this in 1953. So we could just stop here and be like, oh, well, it's not a computable problem. That's too bad. But that seems kind of like giving up. So a natural question is to say, okay, WKL is not a computable problem, but maybe it's not so bad. What additional information would it take for us to be able to solve this problem? Well, the good news is that König's lemma, in terms of information content, is no harder than the halting problem that we saw earlier. And so let me tell you why. So remember, when we were proving König's lemma, the classical result, the crucial part to building our path through our tree was being able to answer the question, are there infinitely many nodes below this node or infinitely many nodes below this one? And this is a question that we could ask the halting problem, and it can answer correctly about it. So let me say what I mean. We can use the halting problem to answer whether there exists some level L such that no level L nodes extending 0 are in the tree T. Well, why can the halting problem answer that? Well, we can write a program which actually goes and searches for such a level. And so this program is going to look for a level L such that there are no level L nodes extending 0. Right? So a level over here. The halting problem knows whether that algorithm is actually going to halt at some point or not. And if we know that it halts, it means that we found some place where there are a level where there are no nodes at that level extending 0. So that would tell us that, oh, there's only infinitely many nodes below over here, so we should go this way. So we can use the halting problem to actually provide enough information to find paths through these trees. In other words, to solve König's lemma. So I'm going to indicate that with, if you know solutions to the halting problem, you can use that to find solutions to König's lemma. So we've seen that WKL is not a computable problem, but that it can be solved by the halting problem. So in terms of information content, WKL, it's not computable. So it has sort of more information content or complexity to it. And the halting problem has at least as much information content as WKL. And in fact, this inequality will be strict. I can't quite say that here, but it in fact will be. So another approach that we could take to calibrating the complexity of WKL would be consider, well, what kinds of problems can it solve? And it turns out that lots of mathematical problems hinge on finding paths through trees if you view them the right way. And the problem that we're going to compare WKL to has to do with map coloring. One natural question to ask is, how many colors do you need to color a flat map so that if two countries share a border, they are colored differently? Well, if you look at this map that we have here, you can see that you aren't going to be able to use two colors because, well, Alcha, Dassel, and Enna all touch each other. They all share borders. So you're not going to be able to use two. But then if you try to use three and color all three of those countries different colors, you can notice that Brivo also borders all three of Alcha, Dassel, and Enna. So you're also not going to be able to use three colors. Well, if you wanted, you could pause here and see, could you do it with four colors? And yes, in fact, you are able to use four colors, and I'll show you that in a moment. People often represent these kinds of map coloring using graphs. And I don't mean the kinds of graphs that you see in calculus, like a graph of a function. I mean a graph that comes from discrete math that's often used in computer science as well. So for this kind of graph, what you're going to do is you're going to take each one of these names of the countries, and you'll shrink it down to the first letter in its name. And then you're going to put an edge between two countries, dots or nodes, if they share a border. So for example, Enna, Alcha, and Docile, their points A, E, and D should all be connected by edges because they all share borders. So if you construct that graph, as I just said, so here's Alcha, here's Enna, and here's Docile, you can see that all three of those countries, I have an edge between them and Brivo. Because remember, Brivo shared a border with all of those. And there's Enna to Brivo over there. So now here is a proper coloring of that map. And by proper coloring of the map or its corresponding graph G, I mean a coloring where whenever you have an edge between two nodes in your graph, say between A and E, between Alcha and Enna, well then those two nodes have to be colored differently. So proper coloring just means that two nodes which are connected are colored differently. And a forecoloring of a graph or its corresponding map is a proper coloring of the nodes that uses at most four colors. So here is a forecoloring of the graph that corresponds to the map that I showed you originally. So now I'm ready to introduce to you the problem stitch that we're going to compute, that we're going to compare to WKL. So let's imagine that I'm given an infinite graph G, and it has vertices, nodes A1, A2, A3, A4, A5, et cetera, et cetera. But in addition, this graph has a very nice property. So for each finite subgraph H of G, there is a forecoloring of H. So let me tell you what I mean by a finite subgraph here. So a finite subgraph of G just means I take finitely made nodes. Let's imagine I take A1 through A5, okay? And I could take any finite collection of nodes. Well, then I look at the graph, which has all the edges between the nodes in that I've designated that were in the original graph G. So this is the finite subgraph. It's sort of marked in the edges are black, and the edges between the other nodes are just gray. Well, and then I'm saying that for each finite subgraph H of this graph that we've been given, there is a way to forecolor that finite subgraph. So for example, here is a forecoloring of that subgraph that I'm looking at here. So a natural question is, you're able to forecolor any finite subgraph of this infinite graph. But does that mean that the entire infinite graph can be forecolored or not? And that's not quite so clear, and let me say why. Because just because I know that I have a forecoloring of, say, this subgraph, and I know I have some proper forecoloring of this subgraph, well, the question is, well, how am I going to stitch them together? Okay. So for example, I'm feeling good about stitching, the colorings for A5 together because they both agree and give the same colors. But then if I use yellow for A3 from this coloring and yellow for A7 from this coloring, well, then I run into trouble because those two nodes are actually connected in the larger graph. And so we would no longer have a proper forecoloring here when we stitch them together. I'm going to call this problem of taking a graph which each finite piece of can be forecolorable, and then finding a coloring that works for the entire infinite graph. I'm going to call that problem stitch because it's the stitching together problem. So your first question would be, is this even possible, right? Just because you have all of these, you're able to color each of these pieces of the graph, who says that you're going to be able to color the entire infinite graph with only 4 colors? Well, we actually have a theorem that says, yes, this is possible. So if you have an infinite graph G, which has this finite subgraph for coloring property, well, then you're guaranteed that there exists a for coloring for the entire infinite graph. But it gets better. We're actually going to be able to show how you can transform an instance of Stitch, take a graph like this, and turn that into an instance of WKL and use that to, in fact, solve the Stitch problem, find a coloring for all of the graph G. So what's our strategy? How are we going to do that? Well, given a graph G, which has this finite subgraph for coloring property, we're going to build a tree, T of G, from the original graph G, so that any path through this tree gives a for coloring of all of G. Then we're going to do this in such a way to ensure that T of G is in fact infinite, because then by the König's lemma, the theorem, right, we know that there is a path through it, and WKL can present us a path through this tree. And then we're going to show how using that path, we have that G has a for coloring. So let's see this process visually. Right? So I'm going to use this notation to say that Stitch as a problem can be transformed into WKL, that problem. And the idea here is that we start with our graph G, such that every finite piece of it is for colorable. And we're going to do something, a computable transformation to it to get a tree T of G. So that for any path F through T of G, well, there's some way to compute from F a for coloring for the original graph G, which I'll call CF. So let's see how to do this transformation. So the first thing that we need to do is define T of G. And a coloring of the nodes A1 through AN will be a node on my tree if that coloring is a for coloring of the subgraph given by those nodes. So let me say what this means in an example. So I'm going to have the node where A1 is gray, A2 is blue, and A3 and A4 are red as a node in my tree, because that coloring is a proper for coloring of the finite subgraph for A1 through A4. And then certainly, since that's a proper coloring, well, then any prefix of that coloring will also be a proper coloring. But as an example of a node which is not in the tree TG, if I color A1 gray, A2 blue, A3 red, and A4 gray, well, that's not going to be a node in T of G because, well, A4 and A1 are connected, so they can't be colored the same color. So let's see what this tree looks like. So I've drawn the tree, a bit of the tree TG for the G example that we've been looking at. And you'll notice right away that this tree is no longer binary, and instead will be at most four-ary, because I'm allowing four colors. So at each level for the next node, I'm having a choice about which of those four colors to color it. But remember, I said that König's lemma actually holds for any infinite tree as long as, it's some fixed arity. So König's lemma still does in fact hold. Well, my claim is that this tree is in fact infinite. And we know that because, well, at any level n, by assumption, there is a for coloring of A1 through AN, and that will be a node on the tree. So that guarantees us that our tree has a node at each finite level n, and therefore we know that this tree must be infinite. Well, hence, because of König's lemma, as a theorem, we know that this tree has an infinite path F through it. I claim that this path F through T of G gives a for coloring for the entire infinite graph of G. And let's see why. Well, suppose it didn't. Well, then that would mean that there are two nodes, AI and AJ, which are colored the same and connected by an edge. Right? Otherwise, F is itself before coloring, we're done. Well, then the finite part of F, you could think about the finite sequence of F coloring A1 through AI and AJ. Well, that couldn't have been a proper forecoloring of just that finite subgraph because AI and AJ are connected. So that means that that node, which is a finite piece of F, wouldn't actually have been node on T of G, which is a contradiction because we were supposing that our path F was a path through our tree. So that tells us that our path F actually, in fact, was giving us a forecoloring for all of G. Let's review what we've seen. So we saw that the stitching theorem is a true theorem of mathematics. It's one of these existential theorems that says if you've got an infinite graph such that every finite subgraph of the graph has a forecoloring, well, then there is some way to forecolor the entire infinite graph. And we proved this result by showing that we could use König's lemma to get a path F through that tree T of G, which encodes a forecoloring of the entire graph of G. So not only is the stitching theorem true, but we've also seen that we can actually reduce the problem of stitch to the problem of WKL knot via one of these problem transformations. And what that meant was that if you have a graph G satisfying that finite subgraph forecoloring property, you can computably get from it a tree T of G that's at most 4 array, such that any path through that tree can itself be computably transformed to obtain a forecoloring of the entire graph of G. So let's review where we've been. So early on, we saw that WKL was not a computable problem. It sort of has more information content than just being computable. But we also saw that its information content was less than the halting problem, in the sense that if you can solve the halting problem, or you know the halting problem, you can use information from the halting problem to solve WKL. And we also showed that stitch not only has no more information content than WKL, but it can sort of literally be transformed into a version of WKL. I think of being able to transform one problem into another as kind of an even stronger relationship between the problems. But certainly it implies that stitch has no more information content than WKL. So these related oracle approaches help us measure exactly the computational hardness of these problems. And it gives rise to a hardness hierarchy of problems, which tells us, well, just how hard is this problem compared to another? So WKL turns out to be at the heart of many other problems from mathematics in the senses that we've discussed. Just as some examples of where WKL is really at the heart of other kinds of problems, it's really what's going on in the calculus theorem that any continuous function on the closed 0-1 interval is bounded. In analysis, it's equivalent to the Heine-Borel covering lemma, which says that given any collection of open intervals that covers the closed interval 0-1, there's a finite subcollection still covering 0-1. In algebra, it's equivalent to every commutative ring having a prime ideal, if you're familiar with those objects. And it's also equivalent to Gödel's completeness theorem from logic, which is the field that I'm in, which says that every countable consistent set of sentences has a countable model. And some of my work in my thesis turned out to also be equivalent to WKL. So recap, what have we seen together? Well, we saw that taking a computable perspective on mathematics is very different than an existential one. We saw that WKL is not a computable problem. We also saw that we could use an oracle approach to measuring the difficulty of various mathematical problems. We also saw that another way to compare problems, even stronger, was this idea of problem reduction. Can you literally transform one problem into another as a way to see that one problem is at least as hard. Now, as I mentioned, I'm a logician, and I should say that this kind of problem reduction has implications for deciding the strength of axioms of mathematics. This is all part of an area of mathematics called reverse mathematics. And the idea there is to see what can the theorem associated with the problem prove. So it's going back to that existential perspective of saying, if you take König's lemma, the theorem that every infinite binary tree has an infinite path, and you took some other very simple axioms, what other theorems of mathematics could you solve? Thank you very much. If you have questions, I hope that you will come to the live in-person part of this talk and chat about these ideas with me. You should also feel free to Google me and send me an email. I'd be excited to hear from you. I also listed here some references, say that you wanted to learn more about some of these ideas. The book that I would first suggest looking at is a fairly recent book by John Stillwell called Reverse Mathematics. And that book is aimed at people who do not have a logic background necessarily, sort of undergraduates. If you wanted to learn even more after that, you could check out this book by Dennis Hirschfeld about reverse mathematics. And then down here are 2 research books on the field of reverse mathematics. Well, thank you very much for your attention and for sticking it out through the end. And I hope to see you at the live portion.